Well, here we are, Module 9, following design principles to build our waveguide. We're going to interpret cutoff.
The not so mysterious thing.
This time we don't have any masks or mystery. The mystery's all gone, and we're going to go further in making it all go away. Here's our result for KZ, and cutoff occurs when this thing is equal to 0. So let's look at the case that we're going to look at a lot, which is TE10, m is equal to 1, n equals 0. That's the dominant mode. And we just substitute in. And we notice that this is just k squared. So that's the free space wave number.
In fact, this is just kx and this is just ky.
Right. Kx squared and ky squared. So we subtract from k. So now, in order to find the guide wavelength, we just take 2 pi over kz, which is this. Straight algebra, and then put m equal to 1, and write, remember that v is equal to f lambda, so lambda is v over f, so this is the opposite. We're in free space inside the guide, so it's lambda 0. M is equal to 1, factor out the pi's, and we get this.
Yep, pretty straightforward. So just to clarify, this lambda is just the effective lambda along the z-axis, right? Because the wave could be kind of bouncing around in a guide. So the lambda, when you just look at the z direction, is not the same as lambda in free space. Is that what we're looking at?
That's exactly right. So there's an effect. And we've seen this before, right? Let's see if we can describe this where the lambda in one direction is bigger. Let's see if we can get a picture that looks like that.
I think that will remind me.
That will remind you of something pleasant we did a number of videos ago. Oh boy, it's rather hot here at the beach, working away on waves. Speaking of waves, where's Sam? Oh, good to see you.
Yeah, I was out in the waves and I got chased by this shark.
You got chased?
But I outswam him. It's fine. Oh, we're filming already, aren't we? I'll tell you the story after.
Okay, well, here we are at the beach, and luckily we have a light board there. So we're going to interpret this result that we did earlier. And we have kx and kz. So we have kx and kz, and the sums of the squares gives you k squared. So let's look at what's going on in the xz plane. So we have kx and kz.
Draw here.
Draw it. So now here's the xz plane. Well, you have kx and kz, so the waves are bouncing back and forth between x equals 0 and x equals a. Right? Because that's the distance of the waveguide. We're cut through here.
Yep.
So the waves are bouncing back and forth. And so we actually see that the waveguide is consisting of bouncing waves back and forth. And you know, while we're here at the beach, I think we've seen this somewhere before.
Yeah, well, didn't we do something about counting crests some time ago? I can't believe the whole beach scenario can apply on waveguides too.
Well, it's exactly the beach scenario. We even had a quiz question where this was water and sand, and what was the wavelength apparent along the boundary?
Right.
And it's bigger than lambda naught. It's exactly the same as what we have here.
Well, this is a great visualization of what we just talked about the lambda g and lambda naught.
Yeah, so we just have simple geometry at the beach. And it's in the xz plane. Of course, there's going to be more complicated bouncings, but this is a simple one because we're doing TE10. Well, I think it's time to go into the water now.
No, shark. We can go have a drink.
Okay, yeah, I don't like sharks.
I can tell you about the shark.
Okay.